All right, good afternoon, everybody. So the topic of today's lecture is it's networking. So we're going to start talking about how do you implement a multiplayer game where the players are connected over a network. I guess just before we do that, though, we should talk about, very briefly, multiplayer games. And so I guess if you've ever played like Mario Kart or something like that, you know that you can have a multiplayer game where the players are playing on the same computer. We're interested in where players are playing on separate computers, separated by some amount of distance. But multiplayer games have been around a long time. In fact, they've been around since the beginning of electronic computers. And so this right there, believe it or not, is an early version of Pong, which you guys implemented in assignment 2. And so this is played on what's called an oscilloscope. I don't think many of you have seen an oscilloscope before. If you have seen one, you haven't seen one this old. Anyway, this is basically an electronic measuring device. Someone figured out how to get a video game working on one of these things. You can see here, there's an early form of a controller, right? And so all your modern game consoles come with their own controllers. That's probably the first controller that was ever created for a video game. Here's an early version of a game that actually ran on a computer as opposed to an oscilloscope. And so this is, what's this called again? Space War, right? Yeah, this is Space War. So this is Space War. This was created for a computer 1960s, somewhere in there. So this computer, you see the screen, but the actual computer itself is this gigantic box that fills up half a room. So it was run on what's called a mainframe. And it had this little display on it. And they're playing this shooter game. So that's a spacecraft, believe it or not. That's the other spacecraft, believe it or not. There's these little dots they shoot out. And so they're basically trying to shoot each other down playing this game. And so this computer doesn't have a keyboard. You'd interact with this computer via what's called a punch cards. So you'd have a piece of paper that you'd punch holes into, and that's how you fed information into the computer. And so instead what they have a bunch of switches on the front of this computer. So physical switches that you would turn on and off. And that's how you would control this game. It turned out to be so popular that people actually started wearing out the switches on these computers. These computers are, in today's dollars, they'd be millions of dollars. So you have to go and replace these switches. And so you can see here that eventually they ended up making controllers so that people could play this game. And so multiplayer games have been games in general have been very popular ever since computers were invented. Multiplayer games came along very shortly after people started creating regular games. And so there's 2 examples of early multiplayer games. All right, so creating a multiplayer game where people are on the same computer, not terribly interesting. Basically, you read 2 or more controllers, and it's a regular game. When the players are connected via a network, it becomes a lot more interesting and a lot more difficult to do as well. Right? And so a network game allows 2 or more people to play together at a distance. All right, so we need I would be remiss if I didn't have a brief history of networked multiplayer games, so you can see the evolution of networked games. And so probably the first, people debate whether this was actually the first networked multiplayer game, but it was written in 1973. So the game was called Empire, and this was written by a student in a course. University of Idaho, I think. Again, the computers at this time, remember these giant computers, they would occupy like a big chunk of a room. And so he wrote this, it's a turn-based tactical game with up to 8 players. Everything's text, right? There's no graphics at this point in time. And he wrote this as part of a course project. It was written for this system called Plato, which you probably haven't heard of. It's now lost to time. Plato was the first computer-assisted instruction system. It's essentially something like OnCue. So it was meant for teaching purposes. You can click on that link if you want to read a little bit more about Plato. Ooh, University of Illinois. So University of Illinois invented this. Plato was invented at the University of Illinois. The University of Illinois is one of the universities where a lot of the foundational ideas in computing came from. So Empire, so that was just basically a course project. Empire 3 actually made it, well, there's an Empire 2, which was written and quickly discarded. Empire 3 actually made it out into the real world. And so it ended up being played on these Plato systems. So these Plato systems, there were, I don't know how many there were across the world. Dozens or hundreds of Plato systems installed around the world, I think. Anyway, Empire 3 became a shooter game and allowed up to 30 players on 15 different teams. And Empire 4 was the first game where online chat showed up. Right? And so these ideas so these things that everybody's used to now in multiplayer games, they have a long history, right? All going all the way back to the 70s. Oh, wait, there's more. Oh, this slide shouldn't be here. Sorry. This is the slide that's supposed to be next. All right, 1975, these things called multi-user dungeons showed up. So in the 70s, this is when Dungeons and Dragons first showed up. So a lot of the early computer games were basically the text versions of Dungeons and Dragons. And so these things called multi-user dungeons or MUDs. So if you ever see the term MUD, that's what it's referring to. These are text-based, real-time RPG games played in a virtual world. That screenshot there shows you something something typical of the time, right? And so your game is just a wall of text, right? In this particular game, if you read it, if you can read it, I'm not sure you can see here that players are coming into the game and leaving the game, right? So here, Iceberg the Necromancer has just arrived, right? And then Iceberg the Necromancer has just left. So this is a true multiplayer game where players can join the game and then freely leave the game at any time, right? And notice the game doesn't crash when they leave. And so 1978, there's actually a game called MUD. Although MUD is also the term that's used in general for these things called multi-user dungeons. So MUD was invented in Essex, so in England. So it became very popular. And again, remember at this time, like in 1970s, people didn't have their own computers. So if you wanted access to a computer, you either worked for a very large company or you were at a university somewhere that happened to have one. And so I guess these were played on these machines called DEC 10s. Did Queens have one of these? Queens had DEC machines, but I don't know if they had DEC 10s. Anyway, and so these games became so popular that basically people would eat up all of the computation power of the computer at the time. So they had to restrict when you could actually play on these games. So here it says that the University of Essex lets people play between 2 and 6 in the morning, or 10 p.m. and 10 a.m. on weekends, right? And even at these hours, the game was always full to capacity, right? So remember, this is just text, right? And you could have enough people playing that it would actually eat up all of the resources of the computers at the time, right? By enough people playing, it's like tens, like dozens, not hundreds or thousands, right? Computing power really has come a long way since the early days of computing. Right? 1978, DEC War showed up. So DEC War is a real-time text-based space battler. So this is basically Star Trek now at this point. So this is, if you even look at the races in the game, they're all based off of Star Trek races. So this was up to 10 players, connected over network. Players could leave or join at any time. DEC War led to Mega Wars 3 down here. So in the 1980s, this concept of pay for play showed up, right? So nowadays, we hear a lot about microtransactions in games. This is not a new idea, right? 1980s, pay for play became popular because in the 80s, most people still didn't have their own computers, right? The home computer had just started to show up. Most people didn't have one. And so companies with spare compute capacity would actually sell you remote access to their computers. Right? And so CompuServe, if you've ever heard of it, CompuServe still exists as a website, but they no longer sell you CPU time anymore. But that's what they used to do. They used to sell you CPU time. Geisco is owned by GE. I don't remember who owned Online. Rapid Data was another one of these companies that would basically sell you access to their computers. right? And so look what they would charge you. They charge you between $6 and $12 an hour, depending on your connection speed. So your connection speed would be between, 300 baud and 1200 baud. So 300 bits per second and 1200 bits per second. It was your connection speed back in the day, right? Most of you probably have gigabit or close to gigabit speed now, right? So billions of bits per second now, right? And you would pay like, I don't know, like $100 a month, right? If you're with Bell or something like that. So now you're paying, back in the day, you're paying $6 an hour for 300 bits per second. And so people would actually pay money so that they could play games on these systems. Right? CompuServe in particular had a bunch of games that you could play. Island of Kesmai is a famous game that you could play. Mega Wars 3, another famous game that you could play, both multiplayer games. Right? Neverwinter Nights. So this is not the, some of you might have played the Obsidian version of Neverwinter Nights. This is not the one. So 1991, the original version of Neverwinter Nights, again, it's based on Dungeons & Dragons, was your first graphical what is MMO or massively multi-online role-playing game. Click that link, you can actually see what it looks like, hopefully.
What do you think of when you hear the phrase,
Let me just click
how
ahead
familiar
quickly.
with play the game?
Oh, here we go. This
Think
was
your
your
monthly
first,
World of Warcraft or Final Fantasy
come on.
the only around
Here.
the edges,
So this is
but
what
it
your
can't
first,
be denied that it gets the job
your
done.
first
Unique to the game was that it
MMORPG
had a time
game
limit
with
attached to
graphics
each
look like.
combat turn, which I imagine was most likely a failsafe to stop one player from hogging the initiative, or perhaps scarce server bandwidth for any period of time, and you
So again, games have come a long time, have come a long way in a relatively short period of time. Okay, 1993, Doom is when Doom showed up. So Doom allowed multiplayers over what's called a LAN, a local area network. So I'll explain what that means in a little bit. Right? So Doom was the first multiplayer first-person shooter that became very popular. Right? And of course, Doom spawned many, basically it spawned this entire, well, Wolfenstein spawned the genre of first-person shooters. Doom was the game made by the same company that came after Wolfenstein. Warcraft, the first version of Warcraft is was one of the early real-time strategy games with up to 2 players over a network. And of course, Warcraft now is, there are many versions of Warcraft, and World of Warcraft is extremely popular still. Right, 1996, a game called Meridian 59 showed up. This was your first 3D, this was your first MMORPG that had 3D graphics. Right, so Neverwinter Nights, 2D graphics. We finally get 3D graphics in the 90s. This is what that game would look like. Kind of clunky, graphics not so great, but it sort of looks like a game now. 1997 was Ultima Online, so this is one of the most successful MMORPGs of all time. You can click on that link if you want to see gameplay from this game. It's not terribly exciting, right? Especially compared to the games you play now. 2004, World of Warcraft, so now we're into more modern games. This is probably one of the 2 most successful MMORPGs of all time. This game's made billions of dollars for, I forget who makes it now, Blizzard, right? It's made billions and billions of dollars for them. World of Warcraft is also notable for being studied by researchers from a wide variety of fields. So this game is so popular that researchers from all sorts of fields related to psychology, people who study human behavior have studied this game and the users of this game for all sorts of reasons. Anybody play World of Warcraft? It's a little bit older for many of you. Okay, so this game is also famous for another occurrence. So there was a boss that you had to, so the way this game works is you'd you'd have these large groups of players called, they'd be parts of guilds. You would go and raid a dungeon of some kind, right? And so the dungeons would typically have a boss in them. There was one boss that would had an ability to inflict your character with a disease. If you were high level, you could actually survive the disease. If you had someone who could cure you of the disease, that would be even better. The problem is if you're a lower level, you'd inevitably be killed by the disease because you'd lose hit points over time. Now the problem is that some of the high level players would leave the dungeon and they would take the disease with them out into the rest of the world. Right? And so remember, this is one world, it's all connected with all sorts of people. And so these high level characters would go out into the world and they would get other people sick. And so this disease spread across the entire World of Warcraft. And eventually they had to reboot, they had to basically reboot all the servers and cure everybody of the disease. Because basically it was killing off everybody who was low level. And so that was actually studied by many, many, many researchers who were interested in the spread of disease. So that's kind of funny, right? Okay, so types of games that involve, types of games that are particularly good for online. There's a bunch of different categories, right? You can have a free-for-all, which is basically player versus player. Cooperative games are players cooperating towards some goal, right? Team-based is basically a combination of these two, right? You have teams that cooperate, and are competing against other teams. Game modes. So what types of games what types of games can you have are applicable to this sort of, to multiplayer online games, right? There's all sorts, right? Everything that you can imagine more or less. So real-time strategy, we've seen a bunch of those. First-person shooters, seen a bunch of those, right? You can have turn-based games, which are still popular, right? So Civ 5 or Civilization in particular is turn-based. Chess, poker, things like that, right? All sorts, these types of games are all turn-based. The requirements that you have for your networking are very different depending on the mode of your game, right? If you're playing chess, you don't care if your network connection is very slow, right? Eventually you'll see the person's move, right? But if you're playing a real-time shooter where everything's moving very quickly, the requirements on your networking are probably a lot more severe. All right, so the third year networks course is not a prerequisite for this course. And so I think Dr. Graham basically ignored all of the network fundamental stuff. But the discussion of networking makes a lot more sense if you know a little bit about basic computer networks. So I've got like a dozen slides here that talks about some networking fundamentals. All right, so what is a computer network? So a computer network is just a bunch of computers. They're sharing resource of some kind provided by what are called network nodes. Right? So a node is just any electronic device that's capable of creating, receiving, or transmitting data over a communication channel. A communication and so nodes are basically, they either distribute information. So your modem that you might have hooked up in your home or apartment, right, that connects out to Bell or Rogers or whoever it is who you pay for internet service, right? That would be a redistribution point, right? So it takes information from your internet service provider and distributes it over your home. Or it could be an endpoint. So an endpoint is something that consumes the information, right? So your computer would be a common endpoint node, right? Your printer, if you have a networked printer, would also be an endpoint node, right? So you might have a network printer, you connect to the printer over your network, you send a document, so you send the information for the document to the printer spits out your document, right? Right, so, okay, so nodes can be, so basically your computer is a node on your network. Right? Now, some nodes are what are called hosts. Right? So a host is any node that participates in an end user application of some kind. Right? So your computer, obviously, you're the end user, so your computer would be considered a host. Your printer would also be considered a host. Right? Things like your modem or other devices that you might have connected on your network, especially the ones that are that govern the infrastructure or that make the physical infrastructure of your network are not generally considered to be hosts. So you often see this term host. Typically when you see this term host, it means the computer. They're talking about a computer. All right, so a networked game is an example of what's called a distributed application. So a distributed application is just a computer application where multiple interconnected but independent computers are coordinating to perform joint computation. There is a fourth-year distributed computing course on the books at Queen's. I don't think it's been taught in some time. I could be wrong, but I don't think it's been taught in a while. So there used to be a course where you'd learn about creating distributed applications. So there are some common architectures for distributed applications. So there's something called client-server, and there's something called peer-to-peer. So both of these are relevant to us when we talk about networked games. Right. Okay, so client-server architecture. So in the client-server architecture, two computers, not necessarily two computers. Well, conceptually, it's two computers. There's one called the client, there's one called the server. Right? So your server is your thing that provides a resource or service. Right? And the client or clients are requesting resources or services from the server. Right? And so if you ever heard of the term web server, that's just a computer that has that hosts a bunch of web pages. Right? So when you click on a link to download to look at a web page, right, you're the client, or your computer is the client. Right? You're asking the server for a particular web page. Server renders a web page, the server sends up returns the information corresponding to the web page, and then your client, your web browser, renders the information sent back by the server. Right? And so usually, in a client-server architecture, the client and server are connected over a network, but that doesn't have to be the case. So it is possible for the client and the server to exist on the same host. So you can set up on your computer, you can have an application that is broken up as a client-server in a client-server architecture, right? And both the server and the client are running on your computer are running simultaneously on your computer, right? When the client needs to do something or needs the server to do something, it sends a message to the server, right? Even though it's on the same computer, right? The server sends information back to the client, and the client does something with that information. Right? And so a picture of this looks something like this. Right? And so a server typically serves multiple computers at once, doesn't have to, right? Or multiple clients at once, but it doesn't have to. So here we have one server. We've got 4 clients. Right? The clients talk to the server. Right? They don't talk to one another in this sort of architecture. Right? So this computer doesn't talk to this computer directly. So here you can imagine that's a web server. Right? And all of these clients are basically web browsers. They're clicking on links that are served up by this particular server. Right? The way this works is your client sends a message to the server over the network. Right? It says, I need something. Right? I would like this web page. Right? Your server computes something, sends the answer back to the client. Right? So for a web server, it basically sends the HTML back to the client. It might have to do some other compute as well. Right? And you can have multiple clients accessing the same server at the same time. Oh, so many games run in this sort of fashion here. So that you have some information about the game being maintained by the server. Right? Clients are talking to the server to get information about the game and then doing something with that information. You can also have what's called peer-to-peer. And so in a peer-to-peer architecture, the work for the distributed application is divided among the participating hosts. Right? A lot of resources will say it's divided equally. That's not necessarily true. And it also say the hosts are all equivalent, meaning they can all do this. All the hosts are capable of doing the same thing. Right? So the idea here is that you're taking work, dividing it over multiple computers. Right? Every host contributes some resources, but each host can control how many resources it wants to contribute. Right? So if you have a low-powered computer, it might contribute less to the solution compared to a higher-powered computer. right? And now the hosts communicate with one another. So as the individual computers perform some work, they communicate the results back to the other computers on the network. Right? And so in this particular situation, hosts are simultaneously clients and servers. Right? They are computing stuff independently, and then they're sharing the information with one another. Right? And so they act as both clients and servers in this case. So in a peer-to-peer network, you've got a bunch of clients, right? And they're all talking directly with one another. Right? So this client can talk to this client, can talk to this client, and it can talk to this client. Right? And so all the clients are able to talk to one another. Or at least they're all able to talk to another client. Right? It's not necessarily that they can all talk to one another. Okay, you can also mash these two architectures together in all sorts of interesting ways. So you can have what are called hybrid architectures. Right? And so here we have a peer-to-peer client server. So here, your clients are all peer-to-peer, right? But they're also talking to a centralized server. So here your clients can talk to one another, right? They can also talk to a server at the same time. So in this particular architecture, the server is acting as a coordinator of some kind, right? It's either storing information that all the clients need, or it's coordinating what the clients are doing, right? But simultaneously, the clients can also talk to one another. So for example, it is possible for this client to talk to that client as well if it has a connection to the other client. Right? And so clients are arranged peer-to-peer, right? But they all talk to a centralized server. Similarly, you can have the situation where all your servers talk to one another, like this, right? And the clients only ever talk to an individual server, right? So now your servers are arranged peer-to-peer, right? But your clients are still talking to individual servers, right? And so here's a situation where the servers are probably computing something that's expensive to compute, or there's many, many, many clients, right? So many that one server can't service all of the clients. And so now the servers coordinate amongst themselves in order to distribute the work between themselves. Right? Clients connect to an individual server to request services. Right? And so games with many, 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 many concurrent online players probably organize something like this. Right? There's probably not just one server for the game. There's probably many, many servers. Right? And the clients connect individually to a server. Right? So StarCraft is an example of something like this, right? There's a North American server, there's a European server, there's a Korean server, a Chinese server, and so on and so forth. Right? So lots of servers distributed over the world. Clients connect to the one that's geographically closest to them, typically. Right? And of course, there's still other possibilities. Right? You can combine your networks in all sorts of different ways. So these are just the four most common. All right, so a network is basically made up of a bunch of hosts or nodes, right? Nodes, sorry, not correct. Nodes, not hosts. So it's made up two or more nodes. The nodes are connected via links of some kind. In a local area network, these are the kinds of networks that you have, or you can have, sorry, when you are connecting devices within close proximity to one another. Right? So for example, all the computers in the computing science building, so in Goodwin Hall, that are maintained by computing, they're probably on what's called a local area network. Right? They're all close enough together that they can be connected onto a single physical network. So in these kinds of networks, the overall capacity of the network, so how much information can be traveling on the network at any one time, is typically relatively low, but the speed is very high. Right? Because the computers are typically all close to one another, there's very low propagation delay. So propagation delay is the amount of time for the first bit of a message to travel between nodes. Right? So imagine you've got a client-server thing running over a local area network. The client sends a message to the server, right? The time it takes for the first bit of that message to show up at the server is the propagation delay. On these local area networks, so in computing science, everything is physically wired. So the information travels over physical wires. So that means the information is traveling basically at the speed of light. Propagation delay is extremely small, right? So probably on the order of nanoseconds, 10 to the minus 9 seconds, right? So very small. Latency is also typically very small. So the latency is the amount of time it takes to transmit an entire message, right? Again, on a local area network, typically the speed is very fast. So the time it takes to send a message is typically very small. Right, so you get both low propagation delay and low latency. You also, transmission times are very predictable on these kinds of networks. Right? Now, a wide area network either connects devices or they connect entire networks across larger distances. Right? Large is arbitrary. Right? You can have a wide area network in a single room. Or you can have a wide area network that spans the entire globe, which is called the internet, right? So the internet is the widest area network that we currently have. Queen's University is probably organized as a wide area network, right? Each individual building or department is probably a local area network or several local area networks, right? These are all then connected to one another via a wide area network. So in these wide area networks, so like in the internet, so the capacity of the internet is very, very high, right? The amount of information you can transmit over the internet is enormous. But the speed is typically lower than what you get over a local area network. Now, as you all know, on the internet, you can have, sometimes the internet is slow, right? You playing YouTube and the video stops and starts, continuously stops and starts, right? Or you're watching Netflix and you watch a very low resolution version of your show as opposed to a higher resolution version of your show. Propagation delay can be variable, right? It depends on how much information is traveling on how much congestion is on the network, right? Your latency can also be variable. Right? So games that run on a LAN typically behave much better than games that run over a wide area network, right? Anybody that's played a real-time game over the internet knows that you run into all sorts of, you can run into all sorts of issues depending on the quality of your internet connection and the quality of all the other players' internet connections, right? If you're playing on a local area network, those problems more or less go away. And so games that operate on LANs typically behave much better in terms of the quality of the multiplayer experience than games that operate over a wide area network. So in the early days of networked gaming, a lot of games were restricted to running over LANs, right? Local area networks. So for example, Doom was restricted to running over a LAN, right? You could only, basically you could set up like in your home, if you happen to have a network set up, you could play against other players in your home. It's also very common to see in universities or schools that had computer labs. Students would figure out how to install Doom on those computers, and you'd have people playing Doom at all sorts of hours on these local area networks run by the university or school. Today, games played over the internet can be pretty reliable, but as everybody knows, they can also be very glitchy. All right, this is going to be relevant a little bit later on. It's not really relevant for today. Every node on a network needs to have an identifier, right? So if you're going to connect two computers, the computers need to know where to find each other, or they need to know how to find each other. So they need to have an address of some kind. Right? So on a local area network, the MAC address is typically what's used. So your MAC address is usually it's a unique identifier that's normally created by the hardware manufacturer. So for example, in my computer, my network card has its own MAC address. That MAC address was set by whoever made the network card. Right. And so these let you address a particular node on a segment of a network. So basically on a LAN. Right? Your nodes are probably communicating via their MAC addresses. Right, so in things like Wi-Fi or Bluetooth, it's the MAC address that matters. Ethernet is another it's probably the most common local area network standard. Also uses the MAC address to connect nodes on a network. When you go out into the real world, so on the internet, for example, it's the IP address that matters, right? And so the IP address is a global address, right? And so the internet protocol uses IP addresses, right? So computers talk to one another using a globally unique address. Right? MAC addresses unique within a part of a network, but not globally unique. Okay, so if you have a software application, like a game, that wants to talk over a network, then typically what happens nowadays is that the application creates what's called a network socket. Right? So a socket's a data structure that basically serves as your communication endpoint. So in today's world, when people say socket, they usually mean an internet socket of some kind. So the internet socket has an IP address, so that means you can uniquely identify it. It has what's called a transport protocol. So the transport protocol is the protocol that's used to communicate information between the two computers. We'll be talking about this a little bit later on in more detail. I guess in today's world, so it's usually TCP and UDP that's used as the protocol. So for example, Unity uses UDP to communicate between two, for networked connected games. And then finally, there's something called a port number that's a part of the socket. So the port number uniquely identifies the connection endpoint on the host and is used to direct the data to a specific service. So there's lots and lots and lots of very well-known network applications, right? So things like email, HTTP, so that's the protocol that's used for the web, right? HTTPS is the protocol that's used for secure web pages. These all communicate over well-known port numbers. Oops, sorry. Right. Port number 80 is the HTTP port. 443 is the HTTPS port. There's a bunch of other very well-known port addresses. So if you click on that link, there's hundreds of these well-known port addresses. So typically, you're not supposed to use port 80 for your video game, right? So if you're going to create a socket, you make the socket by specifying its port number, what kind of protocol you're going to use to communicate information, and the IP address, which is typically the IP address of your computer. Right? So you're not supposed to open up a port 80 for your video game, right? Port 80 is expected to be, most applications are going to expect to connect to port 80. If they're connecting over port 80, it's for the HTTP, right? Hypertext Transport Protocol, right? So for web pages, unencrypted web pages. All right, so that's the very basics of computer networks. Some of these ideas are going to show up a little bit later on when we start to talk about how you're going to implement these in your game. Okay, so so I guess in today's world, almost everybody has internet at home now, right? And almost everybody has high-speed internet access. Right? Certainly anybody living in a large-ish city has access to high-speed internet. Right? 2017, so this is a long time ago now, 84% of Canadian households had access to 50 or 10 megabit per second internet. Right? If you're in Kingston, you have access to gigabit internet via Cogeco and Bell. Right? Even north of Kingston, where there's no, or on the island, so like Wolfe Island or Amherst Island, where there isn't necessarily so Amherst Island doesn't actually have high-speed wired internet out there. But you can get like Starlink, right? And Starlink is pretty high-speed internet. So almost all urban households now have access to high-speed internet. Right? Even rural parts of Canada have access to high-speed internet. I guess fewer if you're in an indigenous community, but that's another story. Right? But access to high-speed internet is becoming more and more common. Right? With Bell, you can get faster than 1.5 gig now, I think. But with Bell and Cogeco, you've got access to gigabit per second internet, right? Even over cellular data, right? Cellular data is very fast, right? Like, nowadays, right? So 5G is like 300 megabits per second. You guys missed the early days of the internet when you would download an image and you'd watch each line show up, right? But right, even on your cell phone now, most people have access to high-speed internet. Unless you're cheap like me, in which case you're down here. But anyway. Back in the old days, you would connect with you'd connect to the internet with what's called a modem. So in the very early days, your modem would run over the telephone line. And so basically your modem would play a series of beeps, sounds, and those sounds would encode the information that you're communicating. Right? And so that was quite slow. So you would get like 28 kilobits per second. Right, and I mentioned earlier that in the early days, if you were using CompuServe or something, you were paying for 300 bits per second. Satellite, this isn't accurate. This isn't accurate anymore. You can get much faster satellite speeds now. Okay, so the problem with the internet, though, is that depending on the two endpoints of the communication, they might be very far, geographically, they might be very far apart. Right? And so even though information travels at the speed of light on these networks, there's still some delay required when you send and receive a message. Right? And so the typical latencies that you will see over the internet, they range somewhere between 50 and 1,000 milliseconds, right? So somewhere around a second or less. Right? There's other issues that you have to consider if you're actually making a game and trying to sell it in the real world, right? Almost everybody has some sort of firewall on their computer. It's usually installed by by your operating system, and you normally don't have a choice, right? Your router might have a firewall on it, right? So the firewall basically restricts what information can flow out and flow into your computer over a network connection. Right. And so your firewall might be set up so that it doesn't allow any external inbound communication. Right. And so this is something you have to deal with if you're a professional game programmer, right? You need some way to, you either have to tell people to turn off their firewall, or you have to tell them how to get around the firewall, or you have to take into account that the firewall might exist. Okay, so what time do we have here? Sorry, 12:12. Okay, so the fact that there is this latency basically affects the player experience. Right? And so there's this thing called state divergence. And so state divergence is, to what degree does the player's interface reveal the true state of the world? So basically, when the player is looking at the screen, right, are they seeing the real state of the world, or are they seeing what their particular computer thinks the real state of the world is, and not what the actual state of the world is, of the game world, right? So there's feedback time, right? So if your player does something, so if the player does something on their computer, right, and their computer has to talk to a server somewhere, the server has to send a message back to the computer before anything happens, right? There could be some time delayed between when the player actually does something and when they actually see that thing happening on in their computer, or in the game, sorry. Right? Propagation delay is the time for a player to see the results of someone else's action. So two players playing over a network, right? Player one does something, right? It might be some time later before player two actually sees what player one did. Animation delay is delay between on-screen updates of the game's object state. And so in many of the way that many games work is that part of the game state is stored on a server somewhere, right? In order for your computer to update the visual appearance of the game, it has to talk to the server to get the game state. The server then has to communicate the information back to the client And then only then can your game actually update the appearance of your game state. Right? And so if animation's involved, you might see glitches or delays in the animation. And finally, there are corrections. So all of these things are more or less inevitable in a multiplayer online game. Right? Because it takes time for your computer, for a client to talk to a server, or for a client to talk to another client. Right? And so if something goes wrong, so if, for example, the state of your world becomes inconsistent somehow, the game has to fix that. And so the fixing part can cause weird things to happen, right? So the corrections can cause unusual things to happen, or for the player to see unusual things happening in their game, right? Okay, so what is, so we're gonna look at all of these things one at a time. So what's state divergence? All right, so you've got latency over a network, right? And so that means it takes time for one player's actions to show up on the other player's screen, right? So state divergence is the difference in the world state or the game object state between the different players' views, right? So notice here, this is not what we want. We want this one. This is what we want. Right? And so here you got two players playing the game at the same time, right? They're both in the same game world. Notice that when they start moving, right? So when Susan starts moving, Susan's character appears ahead of Matt's. When Matt's character starts moving, Matt's character appears ahead of Susan's, right? But these are both views of the same game world. And so these two views are inconsistent, right? Notice that even, is this going to fix? It doesn't actually fix. So notice that, I don't know if when Nick generated these images, he generated them correctly or not. But notice that Matt's character even appears different than it does on Susan's world, right? Here, Matt's got some armor on, and it doesn't in Susan's view, right? So there's a whole bunch of inconsistencies that are happening here. So that's state divergence, right? So the difference in the world state between different players' views. Right? This causes all sorts of problems in these online games, right? So for example, you can end up having an inconsistent game state. So here's an example where this is a dead creature here. So apparently in this game, you're going to loot the creature, right? So here you can see that this creature has strider meat, right? And so if you have two characters, that two different players, they come up to the creature at the same time and loot the creature's body. Both players can think that they've looted the creature, but in reality, one of them has looted the creature first before the other, right? And so because of state divergence, right, both players' clients can think that the body is still available to be looted, so they both loot the body, right? After they loot the body, that information is communicated back to the server, right? The server figures out, oh, it's actually player one that looted the body first. So now the server sends that information back to the both clients, right? And at this point now, the clients have to decide whether or not the problem has to be fixed, right? So player two thinks they've looted the body, player one thinks they've looted the body. The server is telling you only player one looted the body, right? And so now you have to, now this correction has to happen, right? This can be important, right? So if in this particular example, not too important. It probably doesn't matter if they both get a copy, they both get some strider meat, right? But if this is a unique item that's being looted, right? So it's some super powerful, a unique item that has a really high value, right? You don't want both players being able to grab that piece of loot, right? So in this case, it really might matter in some cases. In the shooter games, this causes a huge problem because when one player is looking at their view of the game and they shoot somebody, right, they can see what they see on their screen might be the other player clearly getting hit, right? But in reality, the other player might not be where player one's computer is showing them to be, right? And so in the true game state, right, your opponent might be here, Right? In player one's game state, they might see the opponent being here, and they shoot that person, or the opponent. Right? So they're expecting the opponent to get hit. Right? But in reality, the opponent was over here, and they never did get hit. Right? So the state divergence here causes a divergence of the opponent player, right? Sorry, of the opponent player, and that causes the player one to think that it causes player one to incorrectly think they've aimed at and hit the opposing player when in reality they haven't. And then there's other cosmetic issues that can occur, right? So you've got a scenario where one player changes their clothing, and then latency causes a temporary state divergence, right? So this is what the player sees, right? What other player sees, something else, right? After a few seconds, the game figures out, oh, the player really looks like this, and so now it has to update what all the other players see. So these temporary state divergences typically don't matter, right? So cosmetic state divergences typically don't matter, right? But other state divergences can have a large impact on your gameplay. Right? Is it 2:20? It is 2:20. All right. So I guess we'll stop there for today. We'll continue the discussion on Thursday.